Hello, I'm Dr. Islam, and today we're going to study Venn diagrams and set notation. Our learning intentions for today are to be able to understand what a set is and understand how to use set notation, to represent solutions using set notation, and to be able to use set notation for Venn diagrams. So let's start off. What is a set? So I've got A is equal to curly brackets, -5, 1, and 3. In this example, we have the set A. Here, the elements of the set are the numbers -5, 1, and 3. So sets are a collection of things. They can be mathematical or not mathematical. And the collection of things, the items in the set, are called elements. We use the letter epsilon to mean element. So we could say -5 is an element of the set A. We could say 1 is an element of the set A. And we can say that 3 is an element of the set A. Alternatively, we could say something is not an element of the set. So 0, for example, it's not within those curly brackets. 0 is not an element of A. 100 is not an element of A. And 2 is not an element of A. So in mathematics, a set is a collection of items called elements. So in this set, we have the set A. We use these curly brackets to indicate a set of elements. And here, in our example, the elements of set A are the numbers -5, 1, and 3. Say our answer was x is less than or equal to 2 or greater than or equal to 0, and it was an integer. So what are the possible elements in the set of the solutions? Well, we have got 0, we've got 1, and we've got 2. So our solution set is equal to 0, 1, 2. So with our example of set A, we could draw a Venn diagram. And a Venn diagram is a very simple way and can be very effective to collect and often sort sets. So we can draw a circle and inside put the elements of the set A. So we've got a circle there, and inside we've got the -5, the 1, and the 3, the elements that are contained within the set A. Well, the number 100 is not contained within the set A, so we leave it outside of the Venn diagram. The intersection of sets. Say we had two sets, A and B. The intersection of sets A and B are the elements contained in both sets A and B. So we can write the intersection of set A and set B with the notation intersection as this kind of upside down U. So this means B intersect A is equal to 3. Because in A you've got a 3, and in B you've got a 3. Let's have a look at this in terms of Venn diagrams. So here we've represented our sets A and B as in a Venn diagram. The elements of set A, we've got -5, 1, and 3. The elements of set B are contained within the other circle, and they are 0, 2, and 3. This shaded region in the middle contains the elements that are in both set A and B. So it contains the the number 3. So therefore, the intersection of set A and set B is 3. The union of sets. So in our example, with our set A and set B, the union of set A and set B are the elements of both set A and set B. So we write the union with a big kind of capital U. And so A union B contains minus 5, 0, 1, 2, and 3, because it contains all the elements in A and also all the elements in B. So let's see what this looks like in a Venn diagram. So in our Venn diagram, we've got the elements of set A, minus 5, 1, and 3. And we've got the elements of set B, we've got 0, 2, and also 3. So the elements in the of A union B are all of the elements in the shaded region here. Everything in set A and in set B. Therefore, it's minus 5, 0, 1, 2, and 3. So a set is a collection of items, and it also has two properties. It doesn't contain any duplicates, and the order of the elements doesn't matter, but usually we write the items in ascending order. There can be finite sets and infinite sets. This is an example, and all of A and B have been finite sets. But there's also possibility to have an infinite set. The set of all positive integers or whole numbers is an infinite set, and this is the set is called natural numbers, and we use that n to represent that. And the set of all odd numbers is also an infinite set, and we can construct such a set using 2k plus 1. It's represent an odd number where k is an element of the integers. We also have a further special case, which is called the empty set. We can also have a set with no elements. This is called the empty set. And we can represent it like a 0 with a diagonal line through it. Venn diagrams are very useful of visually representing which items are in the set. So, what does this region represent? Well, this region are the items in A, but not in B. What does this region represent? Well, the items in A and B. Remember, A and B, so it's the A intersection with B. Then we've got, what does the outside region represent? Well, it's items that are neither in A nor B. And why do we have it contained within a rectangular box? Well, the rectangular box represents the set of all items we're interested in. And we use a special Greek letter to represent that. The cardinality of sets is the size of the set. We use n brackets A, or the magnitude, two vertical lines of A, for the cardinality or the size of A. So here, the size of A is 4 because there are 4 elements within A. The size of the cardinality of B is 5. The cardinality of A intersect B is 2 because there are 2 elements in the intersection. And the cardinality of the set that's not contained in A, of elements not contained in A, intersecting with B are 3. This, sometimes you have a dash or to represent not in A, or sometimes you have a C to represent the same thing, complementary set. Okay, so we can also have a set within another set. So A is a subset of B if every element of A is in B. So if we drew the set B, then A would be within it. Now we can use this little C with a line underneath if A is a subset of B where every element of A is in B. Okay, then there's a second type of subset. A proper subset is when if every element of A is in B, but B has more elements. So in this case, you've got B and you've got A, but B also has Y, X, and Z, and so it has elements, at least one element, that's not contained within A. So then we can use this notation A subset B, and it's a proper subset. In the first example, there aren't necessarily elements in B that aren't in A, so A could equal B. But in A being a proper subset of B, A is not equal to B. So let's have a review of the notation we've been using. So we've got epsilon to show that something is an element. So here we've got 2 as an element of the set contain 1 and 2. It belongs to it. Epsilon with a cross means it's not an element of a set. We had this U to represent union, and we had this N to represent intersection, and we had C to represent subset. And it's a proper subset, which means that A is not equal to B.